So finally, we're going to get to nuclear energy and talking about how we can take the energy that's present in the nucleus and this binding energy and convert it into useful forms of energy. We've talked about the particles, alpha decay, beta decay being the main things that go on. We talked about spontaneous fission, where an unstable nucleus will just spontaneously break into roughly half, but not exactly half, into two daughter elements. And then today we're going to get into how much energy is present in the nucleus and then how to turn that into useful forms of energy. So this is a plot of the stability of the nuclei. And so this is the binding energy plotted per nucleon. So a nucleon is either a proton or a neutron. So mass number is the number of nucleons you have, the total number of particles in the nucleus. And this is the thing that until I saw this figure, I didn't understand how you could get energy out of breaking an atom apart and energy out of fusing atoms, right? Because it doesn't make sense. One sense, you're putting atoms together and you get energy out. How is it that you can split atoms apart and also get energy out? Well, because it's not a linear function. There's a maximum in the middle. So the more stable nuclei are right in the middle around iron. It's not necessarily the most stable, but it's right there in that flat plateau. So right in the middle of the periodic table around iron, those are your most stable nuclei. They have the most binding energy per particle in the nucleus. So you could sort of think about their energy state. This is binding energy per nucleon. If you flip this over, you could plot that sort of as the energy of, so if we draw it like this, so this is the energy well that we're in. So these are the lowest energy atoms. And so the heavy atoms are uphill from that, and the light atoms are way uphill from that. And so if we fuse the light atoms, we get energy out. If we split the heavy atoms, we get energy out. Okay. So if that's the case, how is it that stars can create these heavy atoms? Because that's where all of these elements come from. Hydrogen in stellar, space will get slowly over eons collected together, and the hydrogens in the middle can't escape, and the collision rate goes up, the temperature goes up, and gravity, just the mass attraction, is enough to pull these together. And then eventually the inside of those stars, they start ionizing, ripping the electrons off because of the temperature. Then the nuclei and the ions are smashed, then the Coulombic attraction is overcome, and the nuclei start colliding with each other, and you can get fusion. So a star will light when it starts converting hydrogen into helium. And then that generates an enormous amount of temperature and kinetic energy, but it can't escape because there's so much mass. If there's not enough mass, then it won't go anywhere. They'll just blow apart. But if there's so much mass, then that energy can't escape. And then you increase fusion. Then you start getting helium and hydrogen reacting together to make lithium. Then you have lithium and deuterium reacting together to make helium again. And you start building bigger elements by combining whole elements. So we can get to the heavy atoms by basically running spontaneous fission backwards, by having calcium and xenon smashed together to make some really heavy atom. And so all of that's going on in a star. Now, if one of the most stable elements is iron, we could look at the iron that's ejected from stars and kind of get an idea of the age of that star and its development, how much versus the amount of light that's coming out of it versus the amount of iron in that star. So we can kind of gauge with stellar spectroscopy the ages of stars. So all of these elements are made in the stars. Then this is where my limited knowledge of astrophysics fails. The star either gets too dense, something becomes unstable, it'll blow itself apart, okay, in a supernova. And all those heavy elements get blasted out, and then they coalesce and make planets. So that's where the solar systems come from. So after a super heavy star destroys itself, and then the mass is attracted back to itself, you'll get enough mass. What moves faster? The lighter elements. You'll relight a hydrogen helium system star, and the heavy elements are moving slower. They start to coalesce, and you'll start forming planets. So that's where the solar systems come from, and then the planets have these heavy elements in them. And so that's why our periodic table is really the periodic table for Earth, because it has the ratios of isotopes that happen to coalesce to make this planet. So if we get a meteorite that hits the ground and we take it, one of the things we do is look at the isotope ratios and say, oh, this was from some other place, because it's got a different ratio of chloride or chlorine isotopes or something like that. So this is really fascinating. So how much energy is present in this? Well, the masses of the fission products doesn't equal the masses of the reactants. And so this missing mass is called the mass defect. And that's where the Einstein equation E equals mc squared comes into play. So if we just take this very simple fusion reaction, we fuse 2 deuterium atoms and to make a helium atom, and we take the product masses and subtract the reactant masses, we get this mass defect. So the isotope, we got to take into account the isotopic masses. So here's the full, number of sig figs for helium. Okay, and let's see. And this is the full sig figs. There's something wrong here about this. Shouldn't be 22. It should be 2. I think this is a typo. Okay. Oh, it's 2 times. That's what it is. 2 times. Okay. Yeah. So let me erase that squiggle. Yeah, Mr. Princey. Okay, so 2 times the 2 deuterium isotopes, and this is the difference. Now that amount of mass is missing. So if it's missing, it's been turned into energy. So we take that missing amount of mass, multiply by the speed of light squared. So, now we're talking about 10 to the 16 instead of 10 to the 8. And we get 2.21 times 10 to the 12 joules per mole. So that's joules per mole of deuterium burned. Okay. And so we could convert that over to joules per gram. So that's 5.48 times 10 to the 11th joules per gram. Remember, giga is 10 to the 9th, so that's 548 gigajoules per gram from the deuterium fusion reaction. Yeah, so that's a gram, not a ton. And all of those million cubic meters of natural gas or ton of oil equivalent or ton of coal equivalent, we're in the double digits. Well, the ton of oil and ton of coal were double digits gigajoules per ton. And this is 3 orders of magnitude per gram. It's insane how much energy is in the nucleus. So, if we were just to take a ton of TNT releases 4 billion joules. That's why we talk about yields in terms of kilotons of TNT. So this is an energetic chemical reaction to trinitrotoluene. How much uranium-235 is needed to equal a ton of TNT if uranium-235 fission gives this 2 times 10 to the 13 joules per mole? And so that would be 1 gram of uranium would be 21 tons of TNT. So that's about, a gram is a paper clip or a dollar bill. I mean, a very small amount. It's the strongest force known to man and really is an endless supply of energy. We have enough radioactive elements in our Earth's crust that it's just a matter of engineering. That's all it is. We really do not have an energy supply problem at all. But we do have a problem in terms of its destructive force. So this was all developed during World War II. This is a picture of the 100-ton test of TNT. So they had plastic explosives in wooden boxes. They built this huge platform to blow up 100 tons of TNT to test the pressure sensors and so on before they tested at that time, the one nuclear weapon we had built. So they were going to try to test this implosion bomb, and they wanted to measure the pressure and the temperature and all of that stuff. And you only got one shot because you only have one test device. And so they detonated this 100 tons of TNT. And look how big 100 tons of TNT is. It's kind of a grainy picture because this is a report from Los Alamos from 1945. But there's 11 people across here. So 11 persons. That's the diameter. Okay. And then here's the device so the 100 tons of TNT on the left are 20,000 tons of TNT on the right. And you can see Bradbury there standing next to it. This is up in a tower. They winched it up there with chains. And this is the implosion device, the plutonium device that they They knew the uranium device would work. They had two subcritical pieces of uranium, and they detonated one into the other and created the little boy explosion. This is called the Fat Man because it's a plutonium shell that's exploded or imploded on itself. And so it's subcritical when it's out in a thin shell, but when it's exploded in or imploded into a small space, then it's critical. So let's talk about what we mean by criticality. And so this was our 1945 problem. How can you carry this on a plane? You can't. You know, there's a limit to how big conventional explosives can be, but there's no limit to how big nuclear explosives can be. The modern day problem is conventional explosives are limited. This was a Ryder truck full of ammonium nitrate fuel oil, and this is the Murrah Federal Building in Oklahoma City. So this happened, 30 years ago. But I show this picture because of these two chairs here. So I'm going to snip those two chairs out and put them in front of the Sedan crater. So this is the Sedan crater in Nevada at the test site. And this crater was one device, 104 kiloton device, buried, I think they said a few hundred feet under the ground at the perfect spot to create a crater. So why would they want to do this? Well, this was after our nuclear testing system was going pretty well, and we thought, what if we could use nuclear weapons to excavate large amounts of earth, right, to make maybe another canal or something like that, and it would work really well in terms of moving soil. So this was, they sort of analyzed the depth and the explosive ability you needed to get all of the dirt to come out of the hole, right? And if it's too deep, it goes up and comes back down. If it's too shallow, you don't remove as much as you could. So they put it at the optimum depth and blew this crater out. And again, it would, and so I put these chairs on this observation platform to show you the scale. So that you can see the far side of that crater. I mean, this whole picture is the crater. This is the far side over here. And they do tours once or twice a year. So if you ever wanted to do that, it'd be a great place to visit. You can go around and see all these different sites. So that's our modern day problem of nuclear proliferation. If somebody were to get a hold of a nuclear weapon, then they might be able to do this in a city somewhere. And we don't want that, obviously. So that has been the thing that has really held back nuclear power, is the fear of proliferation, that other countries would get the technology to produce nuclear weapons, and then they would be less secure in holding on to them or keeping them secure, and that people would get a hold of them and terrorists would use them against society. So it's almost beyond comprehension. This one was one that was under 90 feet underwater, and this is a 200,000 ton blast. If you watch the video here, this is the Crossroads series of tests, and this is the second shot, the Baker shot. So Crossroads Baker lifted I think it's a battleship. Like there's a battleship in this water column that's lifted out of the sea, and it's like standing on its end. That's how much power we're talking about. Here's a picture of this isn't an actual nuclear weapon, but it's a test piece. So that's exactly what one looks like. This is an unclassified picture, and I can't tell you which one or type it is, but this is when I was at Pantex working with the cleaning side of things, and we didn't clean the outside of we were cleaning components inside, but they were taking some public relations photographs, and so they said, well, you do cleaning, have the technician clean the nuclear weapon. So he's got a little wipe and a glove, and he's wiping the top. So it was kind of funny, but yeah, this is an actual system. This is how they move them around. They have these huge, steel carts to move things around. So let's talk about how we get the energy out of these nuclear, out of the nucleus. And so you have, I kind of like the way this picture's drawn, because this looks more like a water drop, right? Most of the time you see this looking like a cluster of grapes or discrete little nucleons where you have you know, um, you know, 92 protons and 100 something neutrons, and it just looks like a little cluster. Um, and I think it's more accurate, I think, to think of it as a water drop. And so then it stretches, and you can see, if you've ever seen a lava lamp, got one up in the lab, you see these big long stretches, and sometimes when it snaps, you'll see tiny little pieces in the middle that get snapped, and those would be the neutrons. And so this would stretch out and snap, and then there'll be some spare neutrons that get released. And so this is what happens with uranium-235. On average, for every uranium-235 nucleus, you get 2 neutrons. And you say, but wait, I see 3. Well, the initial neutron is also preserved, and so you have 3 come out, but you get a doubling. Every time you burn a uranium-235 nucleus, you get twice as many neutrons out, and that's what allows it to run away. No, because they're sort of stuck in that glob of the other neutrons, and so when it stretches out, the protons are all stuck in these large pieces, and so they're still stabilized by the remaining neutrons. And then when it snaps, then you have some extra neutrons that were between the two that get released. Now, if those spare neutrons exit the mass, then you don't have a chain reaction. But if on average they do hit another nucleus, then you can get doubling and doubling and doubling. And so there's a lot of good videos like this one. Let me see if I can pull it up. I'm gonna pause our recording in class so I don't get copyright strike. Let's see, pull this down. We'll pause that. Yeah, it's going now. Okay, so you saw that neutron control was everything. If you can control the neutrons, you can control the burn rate. Come on. Oh, who knows what I'm doing? I'm clicking around. So one of the way to control the neutrons is just to not have enough fissile material. And so it's a surface to volume calculation there. If you've got so many nuclei in a small sphere, you've got a lot of surface, small volume, and so the chances of the neutrons escaping is high. So in this case, you have a subcritical mass because you have a small mass, and the probability that the neutrons are going to escape before they hit another nucleus is high. But if you get enough layers, you can think of all these masses as concentric rings, right? If you get enough rings, then the chance of that neutron coming all the way through all of those targets and making it out is low. So that would be a supercritical mass. And we can do that with a bunch of different ways. We can reflect those neutrons back in. We can have a larger mass. We can take a mass like the implosion weapons that's spread out into a shell and compress it down into a ball. And so going from a shell with a lot of surface area to a ball with less surface area, then you go to a supercritical mass. And that's how the Fat Man nuclear weapon works. Okay. Implosion was really a trick. If you want to, there's a great movie called The Fat Man and Little Boy. It's about the development of the bombs and the Manhattan Project in Los Alamos. And they talk about trying to turn an explosion, which typically goes out, to an implosion, which goes in, so that they could take this shell of plutonium and compress it into a ball. So they had to figure out how to turn the explosive waves, which are shaped like this, into waves that are shaped like that. So they had to turn a shock wave of an explosive from out to in. And so they did this with explosive lensing, different plastic explosives that have different burn rates. And so they have a fast burn rate explosive that goes out around a slow burn rate explosive, which then would curve that shock wave in. And so that was their trick. And you see them working on that. And some of the German scientists that we helped escape because of the purge of the Jews, they came over here and helped us with that, some of the explosives experts. Maybe even I believe a couple of Russian scientists too that came over to the United States. One of them, the voids in that explosive, they melt casted the explosives into these wedges that were for that plutonium weapon. And there were voids in there. They took x-rays and they didn't want any kind of uncertainty. So he took a dentist drill and drilled into this explosive and poured molten TNT into these voids. So he's holding, a pound of explosives in his lap with a dentist drill. Whee! Into an explosive. And they said, "Aren't you worried?" And he said, "I'll never know." Right? If it goes off, I'll never know. So anyway, pretty brave guy, and he's helped the program. So so this is the first controlled nuclear reaction. We had the first pile reactor in downtown Chicago at the University of Chicago in one of their squash courts. So think about like our racquetball courts. If you've ever been to the racquetball courts in the HKC, something similar to that. You can kind of see this concrete room, and they had all of the graphite, and they had uranium pellets in there, and they had control rods, and they were controlling the neutron flux, and they said Enrico Fermi was impressive because he had calculated theoretically what the energy coming off of this reactor would be. And they said he would plot the next theoretical point with his slide rule, and they'd pull this control rods out, and the Geiger counters would go up to a certain level, and it would be right on his points. Like he had the theory of this nailed, and so everybody was impressed with him. But isn't that crazy that this is a picture of Chicago. Now it's a modern day Chicago, but still the city. This is right in the middle of the city, and they have this experimental nuclear reactor going. So. It was in control. It was not running hot enough to generate a ton of power, but it was definitely a sustained chain reaction. Now here's the Chernobyl design. It also used some graphite moderation, and it's hard to control at low power and can run away at high heat. So if the heat gets too high and the water flashes to steam, the steam doesn't slow the neutrons down as much as the water does, and so it allows the reaction to run away. Basically you lose some of your neutron control. So this is an excellent simulation of what happened. If there's time, we can watch that video, because this guy gets into simulating all of the components of the Chernobyl reactor, and I mean it's a very good simulation. It's about 17 minutes though. So this is we no longer use these boiling water reactors. We have pressurized water reactors where the water can't flash to steam because it's under pressure. So we have, it's pretty expensive though, to have this really thick steel vessels that can hold that pressure. So these are our modern, at least in the United States, our pressurized water reactors. So here's the primary loop, and the primary loop is inside this containment building. So here's the nuclear fuel rods and control rods, and it's heating up this water. It's way hotter than boiling point water because it's under pressure. So we're working our way up that liquid vapor equilibrium line, and so we're not letting it be vapor, it's all liquid. And so when it gets over here to this heat exchanger, this water flashes to steam. So we're just moving the heat from the nuclear core over to this heat exchanger and making steam over here. So the steam loop is also closed, and it's not connected to the nuclear fuel. It's just connected to this heat exchanger. So it's not radioactive. And then it turns the turbine and is recondensed, and it's recondensed using an external source of water. So like a river or a lake. In Texas, we have a lot of lakes that are next to our nuclear power plants. That's the third loop. So the lake or river water is not connected to the reactor core at all. So there's no chance of radioactivity getting into the lake or the river. So you can eat the fish, they don't glow. That's always the joke. You go fishing at a power plant lake, you get radioactive fish. That's not true. So you see our safety system has three cooling loops. The only thing connecting these is the heat exchange. 3 Mile Island, there was a leak in the primary containment, and it spilled out into the containment chamber, but it didn't escape into the environment. it's still a bad thing. I'm not saying it wasn't a bad thing, but everybody talks about, oh, 3 Mile Island. No one died, and we cleaned up the containment room, and it never left into the environment. So we haven't had any releases from our nuclear power plant primary loops into the environment. So how do we do this? Well, the control rods keep the nuclear reaction in check by controlling the neutron flux. So that controls the stimulated fission. So this is how we do it. And so if we and these are computer controlled, they're moved up and down to keep just the right percentage of power output. We want our fuel to last a long time as well, so we want it to burn at a controlled rate, one that also can meet demand on the power grid. Yes. So if we have a nucleus like boron, and I know boron's a good one, xenon is also good, but xenon's a gas. So a lot of these control rods contain boron. So if you look at boron, it's got a really weird molar mass, doesn't it? You got 10.8. Compare that to carbon. Carbon's 12. You have 6 protons, 6 neutrons. Oxygen 16. You have 8 and 8. Nitrogen's 14. You have 7 and 7. You get to boron. That's kind of weird. It's got 5. So if it was 5 and 5, it'd be 10. Boron 10. And so it's boron. It's 10.8. So there's also some boron 11. So boron 11 is a very stable nucleus. In fact, 80% of the boron is boron 11. So 20% is boron 10. But that means that boron nucleus can accept a neutron and not be radioactive. So we can put boron, make control rods with boron, and boron 10 will absorb those neutrons and still be stable. So it'll really cool things down. As it sponges up all those neutrons, then you drop the stimulated fission rate, and everything cools down. So that's what we've got. A meltdown would be if the fuel rods got so hot and then the fuel melted. Why is that bad? Well, then you no longer have the fuel around the control rods. So if this melts down, the fuel pools down here in the bottom, and now there's no controlling the reaction because there's no way to get the control rods in there. So then it gets super hot, and it can, if you did have a meltdown, it could easily breach the containment vessel, and then you have it potentially, well, it would be in the containment chamber, and if it melts through that, then you would have it into the environment. So here's our greatest success story. This is the U.S. Nuclear Navy, and I've updated the numbers. In your notes, you can compare. So we've deployed now over 33 different power plant designs. In your notes, I think it says 27, right? And there's over 273 nuclear power plants for ships. So we've made power plants. We have, I don't know how many we have in the United States, like for electrical plants, but this is quite a few different power plants for ships. Some of those power plants contain multiple cores, and so we have 562 reactor cores that we've made for the nuclear Navy, and over 7,500 reactor years of operation. So that you take the number of reactors we have times the number of years that we've been operating them, that adds up to over 7,000 years of experience. So that also means 7,000 years of experience of people running these things. So the training protocols, the ability to control them, the ability to manufacture them, all of those experience years are captured in just supporting our nuclear Navy. And then we've 171 billion, no, that's million, 171 million miles safely steamed and counting. Think about just the aircraft carrier. Our modern aircraft carriers hold about 6,000 people. Well, that's a good sized town. It has an airport, right? And the airport is, of course, you have to have jet fuel. The nuclear power doesn't make jet fuel, but, bringing in the jet fuel. But the nuclear power makes all of the fresh water for the ship. It, powers all of the systems in the ship, propulsion, everything. So it's heating and air conditioning for the crew, all of that. So today we have 99 active reactors running and 79 nuclear ships. Okay, so they go all over the world. So let's talk about the connection to the environment. So resources refer to the total amount of material available on Earth. Reserves would be what's what's readily available, profitably available. But so there's a difference between resources and reserves, but these change places sometimes. Like sometimes you have a resource that's not profitably extractable, okay? But then whenever technology comes along, that resource now becomes a reserve because now it's profitable to extract it. And you've heard, at least in your lifetime, this shift in terms of shale natural gas. So for years we knew that shale natural gas was there. So it was counted as a resource, but it wasn't profitable to extract it. And then we got into hydraulic fracking. So you drill into that shale and the natural gas percolates through the rock, but slowly. So you can drill into a shale formation and the natural gas will come out, but it'll come out too slowly to do anything with it. You know, it doesn't have enough pressure to generate an income stream, right? It's not going to come out of the well very fast. So what they do is they get into that rock formation, then they plug the pipe on the top end. It's a horizontal well, but they plug the exit, and then they pump fluid in there at extremely high pressures, and it'll crack that rock formation and create a huge amount of surface area in the shale rock area. And so now, because of the new surface area, the natural gas molecules that are trapped in that shale deposit have a shorter distance to migrate through the rock. And so they'll migrate through the rock into the fractures, and then they'll make it out at a profitable rate. So that turned natural gas and shale natural gas from a resource into a reserve. Now it's profitably extractable, and it's really deep. These are not near the surface, so these are really deep. When people worry about subsidence craters and things like that, this is deep enough that we're not going to have surface effects. Increased earthquakes. I've heard a lot of things associated with this, but there's little evidence that that's being caused by fracking. Now, this is all connected. If we want to do the resources and reserves for energy production, it's connected to the environment. So there really is no such thing as zero impact or zero emissions. We have to balance these things. And in fact, our switch over to natural gas and a lot of our electrical generation has reduced the United States carbon output a dramatic amount. So it's been an important factor. So here I took that total energy landscape that we had talked about earlier and converted everything to exajoules, and now put the uranium on here. So we have 9,000 exajoules of useful uranium in our country to manage our energy landscape. This is just showing that coal, oil, natural gas is all going to continue to play a role in the foreseeable future. Biomass is really not easily increased, but notice how solar, that's a huge potential because we saw how much energy the sun hits us with. Okay, now they're showing nuclear power tapering off. I don't really agree with that. This was put out in 2003. I think nuclear power, the attitude around nuclear power has really changed a lot. So I see that as growing. So there really is no global supply problem of energy. We have enough energy in the globe to go for thousands of years. But the reserves aren't shared, they're sold. And so they still have an economic issue. Who has what source of energy? If we're going to go nuclear, who has the will or attitude to turn that into nuclear weapons, and would they send those out with terrorist organizations? So that's where you see on the nuclear stage this pressure against Iran and so on, and the distrust, not just by the United States, but many in Europe and other places in the world, and even Saudi Arabia, against a nuclear program there. But those are all political issues. It has nothing to do with how useful and profitable nuclear energy is for generating energy. So yeah, economics and politics plays a huge role. Now we talked a bit about pollution. Let's talk about what happens after the nuclear reactor has been burned for a while. We get all those daughter elements. So if I split uranium and it makes we said early on it was like a barium and a krypton. So now we have these crazy isotopes of barium and krypton that are they have way different number of neutrons than the natural ones we see on here. So they're highly radioactive. And so then the initial spent fuel is extremely radioactive and deadly. So we pull that out of the reactor and we set it in a pool. We talked about letting those cooling pools cool it down until we get to the longer half-life elements. We can do two things from that point. We can take that fuel and we can go to a reprocessing site and we can pull out the other useful elements. We probably put in uranium fuel, and now that, depending upon the neutron flux, has other elements like plutonium in it, which can also be used in reactors. And so we can extract out the remaining uranium, maybe some other elements that are useful, and reprocess that fuel. Get rid of the less useful elements, and we'll see what we do with them in a second, and then rebuild fuel from spent fuel. If we did that, we would go, like even in the United States, I calculated that we would have 16,000 years of nuclear energy to count for our 100 exajoules per year. So we would have an enormous resource there. Even if we just did first pass, we have hundreds of years. So what do we do with the waste? Well, this is the best definition, I think, for pollution, because it has three components that you can work with. And so it's a loss of control of a concentrated substance that causes harm. That would be what you would use to define a pollutant or pollution. And so what we do is we focus on control. So if we can control the substance, if it's concentrated and causing harm, if we can control it, then it's no longer pollution. And solids are the easiest to control. And so what we have here is vitrified waste. So what we do is we take sand, basically we make glass. We melt sand. There's no shortage of sand. Okay, so we mix the daughter elements of fission and so on in with sand, heat it up, melt it, and form a glass. And then we cast that into, waste pellets, rods, whatever form they make. We basically make these clumps of glass that contain the radioactive elements and then store them while they decay. Okay. And it's a solid. It's something that can be monitored. You can swing by and with your little Geiger counter say, yeah, the waste is still there. It hasn't been stolen. If it is stolen, that's a pain in the butt to get those radioactive nuclei out of glass and then concentrate it and pick out the bits that are useful for a bomb or for nuclear power and throw away the bits that are not. So it's sort of working against proliferation too. You vitrify this waste, it's really hard then to undo that process. And then where do you store it? Well, we have a salt mine in Texas that's there for storing the waste from the Department of Defense, but we don't have a public sector waste disposal site. They tried to do this at Yucca Mountain in Nevada. And immobilization is the key. There's been nuclear reactors on Earth before. There was a natural nuclear reactor in Gabon, West Africa, which is crazy. It was just a mountain that had a critical amount of uranium in the rock deposit, and it was there close enough that it was going critical for many, many years and generating all of the daughter elements that we see from nuclear waste. So we're geologists, I don't know how they came up with this, but geologists found this deposit in this country and said, wow, this looks like several, years ago, this nuclear reactor was going, because we have all the daughter elements that we have in our spent nuclear fuel. Isn't that strange? So when they say that uranium is the highest naturally occurring element, it's actually not true, because they found plutonium and americium and so on in Gabon, West Africa, where this natural nuclear reactor was going in a geological formation. Anyway, so now we have the WIP plant, the Waste Isolation Pilot Plant near Carlsbad for defense-related waste, and it's vitrified waste stored in a salt mine. I thought this was great that Yucca Mountain was being prepared to store the civilian power plant waste, but it just ran into political problems for decades, and eventually they just killed the whole project. Um, they had some, I think, ridiculous criteria for the environmental impact. They wanted to guarantee with the environmental impact study that the public dose at the fence line would be below background for 1,000,000 years. And that's a little ridiculous. We don't have the technology to make a facility that would last 1,000,000 years. And so they were saying, because we don't have that technology, we can't open this plant. And it seems like a sort of a false dichotomy, because if we don't open this plant, even if we can't guarantee it'll be safe for 1,000,000 years, we have to store the waste in the various cooling pools near the cities where we live in a form that's not as stable as this. So it's a huge back and forth. There's been scientists that have been politicized on both sides. It's really disappointing to me that we haven't been able to open a civilian waste repository. Sweden has, a couple of other countries have civilian waste repositories, but we in the United States haven't. And I think the political side of this, the people that are just against nuclear power, they're basically saying, if we can stop up the tailpipe, then the engine won't run. And that's a common trick in the 50s and 60s, when my dad would always tell me, yeah, we stuck a potato in my friend's tailpipe and he's trying to start his car and it won't start. Or maybe if it kind of starts a little bit and he revs it, it'll blow the potato out and get this big bang. And I mean, it's a funny joke, but the analogy is true. If you can stop the ability to get rid of nuclear waste, then you get a problem with the whole infrastructure, because how can you run these plants and continue to generate waste if there's no safe place to put it? So that's where the political battle is being waged right now. And to put that in perspective, it's really crazy. They're worried about this Yucca Mountain facility when right there at the same site we have the waste from 99 atmospheric tests and over 800 subterranean tests. So you see these craters here? These are underground explosions that cause these subsidence craters. Every one of these. So every one of those was an underground nuclear test. And there's no containment vessel around the daughter elements of those nuclear detonations. And so if there's going to be any environmental damage to Nevada, it was done between 1950 and 92 when we stopped doing nuclear testing. And it was 92, sometime in the 90s. So it seems politically ridiculous to me that we can't open some, maybe Yucca Mountain's not the one, but we should be able to open some civilian, power plant waste, because it's crazy. So that's it. We're out of time, but hopefully this, the one thing that's not included in this lecture that should be is the new fast salt reactors, the thorium reactors and the salt reactors, because they generate much less waste. It's impossible by the way they're designed to have a meltdown and so on. So if you're interested in this, shoot me an email, or I'll post to Blackboard some good videos on the thorium reactor, because that's generating a lot of interest. And now there's a company too that took some engineers out of the nuclear navy have formed, called Nano Nuclear, and they're making modular reactors that are about the size of a semi-truck that can be dropped into place to run a nuclear power plant. So the nuclear power plant is the size of a semi, 53-foot trailer. And they're trying to get the EPA and the atomic regulatory bodies to approve them for use at remote sites. So they'll try this at remote sites first. But I bet we're going to go that way if I'm a betting person, for things like Bitcoin mining or remote energy production on the northern slopes of Alaska and places that are away from civilian centers. Because if there is a problem with these reactors, again, there won't be anybody around necessarily to have a huge impact. It wouldn't put it downtown Houston yet. If they prove they're safe and can run for many years like they have with the Navy, then we can have modular reactors all around the city, and then hurricanes and tornadoes won't knock down our transmission lines, and it'd be a smaller grid, and a more robust grid. So that's what I predict to the future, these modular reactors showing up at different places, and then shorter transmission lines to the users. And so we'll have a more modular grid of electricity and a more robust grid. So I think that's something that we can look forward to.